In this lab, my partner and I explored how water behaves under different physical forces through 4 experiments. We investigated surface tension, cohesion, buoyancy, Archimedes' principle, and Newton's third law. I'll explain what we did and the physics behind what we observed. In this first experiment, we gently placed a paperclip on the surface of water using a small piece of tissue. After the tissue sank, the paperclip remains floating. Even though the clip is made of metal and is denser than water, it doesn't sink. Surface tension is responsible for this. The surface of water behaves like a flexible membrane. As long as the surface isn't disturbed, it can support small objects. In our second experiment, we shaped clay into a compact ball and placed it in water. It sank immediately. But then we reshaped the same piece of clay into a wide, hollow boat shape. This time, it floated. This demonstrates Archimedes' principle, which states that the buoyant force on an object equals the weight of the water it displaces. The clay ball displaces only a small volume of water, so the buoyant force is less than the weight, causing it to sink. When shaped like a boat, the clay spreads out and traps air inside. It displaces a larger volume of water, increasing the buoyant force. When the buoyant force equals the weight of the object, it floats. This shows that the shape and displacement determine floating, not just the material. We then went further and decided to test how much weight our boat could really hold, with pennies. One by one, we placed the pennies on, and it didn't capsize and sink until 7 pennies later. In our next experiment, we call this the ghost weight. We placed a cup of water on a scale and recorded its weight, but then we lowered an object into the water without letting it touch the bottom or the sides. Even though the object wasn't resting on the cup, the scale reading increased. This demonstrates Newton's third law. When an object is submerged, the water pushes upward on it with a buoyant force. In response, the object pushes downward on the water with an equal force. The downward force is transferred to the cup and measured by the scale. The increase in the scale reading equals the weight of the water displaced by the object. In our final experiment, the penny dome, we placed a penny on a flat surface and carefully added drops of water one at a time. We counted how many drops the penny could hold before the water spilled over. Instead of spilling immediately, the water formed a raised dome shape above the surface of the penny. This happens because of surface tension. Water molecules attract each other through cohesion. These cohesive forces create a tight surface layer that acts almost like an elastic skin or a membrane, as I said earlier. As more water is added, surface tension holds the molecules together, allowing the dome to grow higher than the edge of the penny. Eventually, gravity overcomes the surface tension and the dome collapses. Our penny specifically was able to hold 30 drops. But then we repeated the experiment with soapy water, and fewer drops were able to fit on the penny. Soap is a surfactant, which weakens the attraction between water molecules, and with weaker cohesion, the surface tension decreases and the dome breaks sooner. These experiments show how water responds in different forces. Surface tension and cohesion can hold objects up. Buoyancy lets shapes float depending on how much water they push aside. And submerged objects still transfer force through fluids. Even in small experiments, we can see how physics explains the behavior of everyday materials like water.